So this is a joint work with Rodrigo Veiga, Bruno Loureiro, Florent Chakala, and Lenkas Deborova. And the basic setting is just a teacher-student model. So we have a teacher that is a two-layer neural network, and we want to learn it with a student, which is another two-layer neural network. And we do that through the classical stochastic gradient descent algorithm. And it's a very well-studied topic, and there are basically two main lines of study for that. And the first and oldest one is the so-called SAD and SOLA approach, which mostly works in the high-dimensional setting and approximates the dynamics of the learning with a differential equation. And on the other hand, when the average number of neurons is large and the dimension is usually fixed, you have the mean field approach, which approximates the neurons by a measure in RD, and then approximates dynamics by a partial differential equation on this measure. And our goal here was to basically bridge the two approaches between the settings P much larger than D and P much lower than D. And the main observation for that is that everything in this kind of networks happens through what you would probably call pre-activations, and what the physicists usually call local fields, which are simply the scalar products between the weights of the teacher or the student and the data points. And if the data is Gaussian, that we assumed, then those pre-activations are just also jointly Gaussian, and we are only interested in their second moments to know anything about them. And their second moments are just scalar products between the teacher vectors and the student vectors, or the student vectors and the student vectors themselves. And so this gives rise to what we call a macroscopic state of the network, which is simply this second moment matrix. And this encapsulates basically everything that we would want to know about the dynamics of the network. And since it encapsulates everything we want to know, in particular, it encapsulates its own update equation. So we can write the value of omega at time t plus 1 as a function of the value of omega at time t plus a random noise coming from the data randomness. And we showed that as the dimension goes to infinity, this dynamics converges to a deterministic differential equation on omega, which is standard for, let's say, Markov processes. And we got non-asymptotic bounds on it that allows us to take P growing with D in a quite large fashion. And if you take a look at the update equations for omega, we can notice that there are two terms that I've highlighted. The first one is a learning term, which is the one that's going to drive the equations to the global minimum. And the second one is a noise term corresponding to the noise around the population loss. And those two terms have different prefactors in front of them. One has gamma over PD, and the other has gamma squared over P squared D. And so by tuning the values of gamma and P, we can tune the relative strength of those prefactors, which gives rise to a whole phase diagram of learning. And if I go through the phase diagram starting from the bottom left, you first have a region where just the time step goes to infinity. So you basically, your dynamics are basically pure noise. So that you have no ODE approximations for it. And then if I grow a bit the factor gamma over P, I get in a place where I can track the learning with ODEs, but the network will just not learn the teacher. The noise term will dominate, and I will have no risk decreasing. Then, coming a bit after, I have the plateau phase, where I have some learning because of the presence of the learning term, but then the noise term will prevail, and there will be a plateau that I cannot get out of. And finally, if I either overparameterize enough or choose a sufficiently small learning rate, I have a setting where the learning term dominates, and which basically reduces to gradient flow approximations. So depending on both the number of hidden neurons and the learning rate of the network, you can have wildly different regimes, and it also shows that, for example, overparameterization does help in learning, at least for two-layer neural network. Thank you for your attention.